will just begin by recalling some of the algorithms from last time. So, one was this thing called row insertion, and what you have is a row u and a letter A, and you insert this and you get A prime comma u prime. And how does this work? So, so if u is u is a row, so it's like I'll draw it like in this tableau kind of this thing. So this is my u, and I'm trying to insert A into it. So I look for the leftmost letter AI, which is strictly greater than A. So that means that this is strictly greater than A, and these guys are less than or equal to A, right. If such a thing does not exist, I just make A sit at the end of this, right. But otherwise, I look for the leftmost letter that is strictly greater than A, and then I take this A and put it in here. So, I will draw the output, and then this A I gets bumped out. And then what I did was, I applied this to a tableau. So, now I was thinking of a tableau in two different ways. One is as a word, a special kind of word. You take its row decomposition, and then you have this dominance condition between the rows. And you can also describe a tableau as a picture, where you have a Young diagram and you put numbers into the boxes. So, in any case, when you have this picture, then you read it from left to right, but starting with the bottom row. So, then we had this notion of insertion of. So, I have a word W, which is a tableau, and then I have this notion of inserting. Okay, and what I want to say is the following theorem. So, you take tab lambda A n cross A subscript n cross A subscript n, and what you do is you take a W comma A and you send it to the insertion of A in W. Now, what will happen is that so what you do is, when you have a tableau in general, let us say you have a tableau like this, and then you insert A in here, and it takes some A I and it bumps it out, right. So, what you do is then you try to insert this A I in here, and then it takes something else, maybe B j, and bumps it out, and then you take that B j and try to insert it here, and so on. At some stage it may just so it is possible, say you have one more thing, it may just come and sit at the end of a row, or it may keep bumping stuff and going into the next row. And so, what will happen is, at the end of this process, you will have added one box somewhere to this tableau. So, what you will get is a function from this to union over all mu in lambda plus, which means the set of the shapes which are obtained from lambda by adding one box somewhere. So, this is a bijection. So, So, in order to prove this, I need to establish two things. Firstly, I need to establish that this is itself a tableau. So, basically what I want to do is this is disturbing some part of each row and then some part of the next row and so on. I will just take two rows and see what happens, and then I can do it's recursive. So, then the next two rows will be taken care of in a similar manner. Okay. So, but I will just give you the gist of the argument. So, the gist of the argument is that when you put this A in here, then it will bump out something. The thing that it bumps out is greater than what you put in here, and using that you can show that what it bumps out here will be either in this column or to the left of it. And also you know that what you are trying to put in here is greater than what you try to put in here. Using these two facts, you can show that the column order will be strict in this case. And the other point is, how do you reverse it? So, reversing rests on the fact that this row insertion itself is invertible. So, how do you invert row insertion? So, now this is still less than or equal to A, less than or equal to A, but over here I know that this is greater than A. What?
Is that meant to be a bijection?
Yes.
Then you need to distinguish one of the cells of mu.
So, that is distinguished immediately when I say mu is in lambda plus. Okay. So, yeah. So, where was I? Right. So, the invertibility of row insertion. So, now I know that this guy got bumped out. I want to know where did it get bumped out from. So now let us understand what is the relation between these things and A I. So, these are less than or equal to A I in fact, and this is greater than A I, and A itself is greater than A I. So, all I need to do is to find the leftmost position where I have something greater than A I. Oh yeah, this is less than, this is less than or equal to A I, this is greater than A I, this is fine. A is less than A I, that is right. So, okay, yeah. So A is, this is less than or equal to A I. Oh yeah, this is the leftmost position where this is less than or equal to, okay, this is less than or equal to A, less than or equal to A, less than or equal to A I, and then here they are greater than A I. A is less than A I, yes, yeah. So, this is A is less than A I, and these are all less than or equal to A, so these are also less than A I, and these are greater than or equal to A I. So, I look for the leftmost position where I find a letter that is greater than or equal, no, I look for the rightmost position where I have something less than A I, and that would have been what was inserted. So, this process is reversible, and for that reason this thing is also reversible. Let me explain using an example. So, let us just look at let us say lambda is 431 and mu has to be in lambda plus. So, let us say it is 432, and let us say I have this tableau 1, 2, 2, 4, 3, 5, 7, 4, 6, and I want to know. So, this is something on the right hand side, and I want to know uniquely where it came from, right. That would be constructing the inverse map. So, firstly I figure out what changed in the shape. So, what changed in the shape was that we added this box, right. So, that means that I had inserted a 6 here and it just came to rest on the right of this row. So, where did this 6 come from? Well, this 6 must have been bumped out from here, right. Who bumped it out? Well, what was the rule? I look for the rightmost element that is less than 6. So, this 5 bumped out the 6. So, at the previous stage I must have had right. So, this 5 must have been bumped out from somewhere here. So, I must look at the rightmost stage where I have an element less than 5, and that would be the 4. So, this 4 bumped out the 5, and so I would have 1, 2, 2, 5, 3, 6, 7, 4. This is what happened. So, this the entire process is completely reversible, and so this is a bijection. So, this is a similar dual theorem. I will write it like this: A n cross tab star A n to is a bijection. So, this was what I called column insertion. So, these are two different bijections. So, this, as you know, is the same as tab we saw that both these are depicted by the same picture. Maybe I should put a lambda prime here. Right, and so if you replace lambda by lambda prime here, these two are bijections between the same sets, but they are actually different bijections. Okay, so, these are two different bijections between the same sets. Both these bijections have a nice application to symmetric functions. Okay, so let me remind you what is tab star A n. So, these are different when we think of them as words. So, a word is called a dual tableau if you have W and you can write it as V1, V2, V k, where these are columns, and this is called the column decomposition if these are maximal columns. So, if you concatenate two of them, it is not a column anymore. And then there is a column dominance condition. So, you have column 1, which is say U is equal to A L A 1 and V is equal to B M B 1. Then we will say that V dominates U, column dominates U if firstly M is less than or equal to L, and secondly B I is greater than or equal to A I for I equals 1 to M. Visually it is just something like this. So, you have your first column, which is written like this: B A1, A2, no sorry the other way around, A1, A2, A3 and so on, AL, and then you have your second column B1, B2 and so on up to Bm. You are saying that this column is not longer than this column, and you are saying that each entry of this column is greater than or equal to the corresponding entry of this column. So, it is like a comparison of two columns in a tableau. So, which is why both these things give the same it is a set of words. So, we have two different sets of words which correspond to the same figure, which is the semi standard Young tableau that we like to talk about. Yeah. So, you read the, to convert a tableau into a word, you read it by columns from bottom to top, left to right. So, that is called the column word. Now, recall that we had this S lambda.
You said there are two bijections. Which are the?
This is one bijection, this is another bijection.
They are between different. Okay.
Yeah, but if you replace lambda by lambda prime, then this becomes the same sets, but these are actually different bijections. Okay. So, S lambda, we will see when we generalize this a little more, we will see how they actually give, but at this stage they give the same identity for symmetric functions. So, I am going to write S lambda for brevity. This really means S lambda in x1, x2, xn. Okay, I am fixing throughout this lecture n, which is the number of letters in the alphabet. The shape of the tableau is the lengths of the columns.
Okay, it's not like the column lengths are not the column lengths.
They are the column lengths of the tableau.
Then why is it tab star lambda dash? Because you get column lengths which are the column lengths of lambda.
Right, but those are the dual of the row lengths. Yeah.
Then when you apply this one, then it goes to lambda dash plus.
Yeah. So, here they are both lambda plus. So, there if you put, so what you will get is if you replace lambda by lambda dash, then you will get lambda dash plus. So, maybe you are asking whether lambda dash plus is the same as lambda plus dash. That means you are adding a box to lambda dash. Okay. Otherwise, what you could do is you could take one of these mu in lambda plus and take its dash. This is a set actually, I am saying element wise dash, but it is the same whether you first conjugate and then add a box, or you first add a box and then conjugate, it is the same, because you just add the box in the conjugated position instead. Okay, so, at this stage these two are giving the same sets if you put. So, here if I put lambda equals lambda dash, then I get a n tab lambda dash star mu dash belong to lambda dash plus tab mu dash star a n, right. I have just replaced lambda by lambda dash, but then this is just tab lambda, right, and this is just tab mu, and then all you have to convince yourself is that this is the same as this. Okay. So, now recall this Schur function, which is finally the thing that this entire workshop is interested in. This and its generalizations is the character of irreducible representation of GLN. So, this is remember this is defined in terms of tableau. So, this by definition was right. So, if I apply this valuation to both sides of this thing, then what do I get? So, yeah, so this is and in particular S1, what is S1? This is just x1 V of w, thank you, and S1 is just this, because if you want a tableau of shape 1, then you can just put one of the numbers 1 to n in here. And so, the weights add up to x 1 plus x 2 plus x n, which is also the same as E 1, which is also the same as H 1. Okay, so, so if you apply the weights to all these things, what you get is the following identity. So, I will call it Baby-Pierre's rule, which says that S lambda S 1. So, this is when you apply weights to the left hand side of one of these identities, right, is equal to sum mu belongs to lambda plus S. And in terms of representation theory, this using Frobenius reciprocity corresponds to the fact that if you take the representation of if you take no, okay, yeah. So, what it says is if you take the representation of V lambda and tensor it with the representation corresponding to 1, which is just C n, the natural defining representation of G L n, right, then this is so this is the representation theoretic manifestation of this. So, maybe I should just it's probably been discussed in some of the other courses, but I will just give you the dictionary here. Sorry? Yeah. Yes. So, well, okay. So, so there's some conventions here. Let's make those conventions. So, when you do these kinds of things, you have to understand firstly that if lambda has more than n parts, then S lambda x 1 x 2 x n, what is this going to be? So, it is a sum of semi standard Young tableau of shape lambda in the letters a n. Now, suppose this has more than n parts, right, then look at the first column of the tableau. You have only n letters. So, you can't put them in, you can't have an increasing sequence of length more than n, which is the first column, right, you can't have a strictly. So, then this becomes 0, and and whatever universal constructions are there for this representation, they also become 0. So with that in mind, these are perfectly sound formula. So you don't get non-zero Schur polynomial for all lambda, you only get them for lambda with parts with less than or equal to n parts, and that those actually form a basis for all symmetric functions in n variables of degree whatever size of lambda. So that's the representation theoretic interpretation of these things. Now what I want to do is I want to sharpen this a little bit and see what happens when you insert say a row or a column sequentially. So now the theorem I want to state is the following, that if you take tab lambda a n cross, and now I will just use a notation that I introduced last time, r k a n. So let me remind you what this is. So r k a n is the set of all rows of length k in the alphabet a n. Okay, so r k a n consists of weakly increasing words. And what will this bijection be? Well, so let me tell you, and you will get so the condition is mu minus lambda is a horizontal strip. I need to explain what this is. And what is this function? The function is given by w comma a1 a2 ak goes to, so you take w, first you insert a1, then you take the result and then you insert a2 and so on. And finally you insert ak. So you sequentially insert these numbers, and what it is saying is, of course, so when you do this, you will get a bunch of, you will get a new tableau, right? But the condition here is saying that so let me say that so this tableau mu will contain the tableau lambda. Its Young diagram will strictly will contain the Young diagram of lambda, and in fact it will have k more boxes because we added we inserted k things, right. And what will happen is that this horizontal strip condition says that no two boxes of mu minus lambda. So, this means mu which is not in lambda, mu complement lambda. So, I mean, I guess set theoretically this dash should be the other way, but they always write it like this. No two boxes of mu minus lambda lie in the same column. So, let me illustrate this with an example of what these horizontal strips are. Yeah.
There should be condition on maximum number of boxes and mu.
Yeah, of size k. It's completely fixed because you're inserting k things, the number of new boxes will be is a horizontal strip of k boxes. So, this is the horizontal strip condition. So, let me give you an example. Suppose you take lambda equals, say, this favorite partition of mine 4 3 1. And let us take k equals 3. So, what are all the ways I can add a horizontal strip of length 3? So, the only condition is, so the first box I have several ways of adding it. I could add it here, or I could add it here, or I could add it here, or I could add it here. I have 4 choices for the first box, right? And then for each of them, I have certain choices for the second box. So, suppose I added the first box. So, anyway here, so suppose I chose this option for the first box. So, this is my option for the first box. So, and say this was my, sorry, these are not there, right? 4, this is okay. So, suppose I have added my first box here and I added my second box here, then I cannot add the third box here because it would violate the horizontal strip condition, right. But I could maybe add it here, this is allowed, this is allowed, right. I could add one box here, one box here and one box here, that would be a horizontal strip. So, let me explain why this is true. So, the main thing is you have to use the fact that this is a row, and so you have to understand what happens when you keep inserting numbers which are in weakly increasing order. So, I have introduced here some number, let us say let us say I started by inserting a number a in here, right. Then it is going to bump out something a1 and some path it will take. So, maybe it will bump out something from here, which will then bump out something from here, and then maybe it comes to rest over here at the new box. This is the new box. Okay. So, this is my, let us say a1, and now after this I want to, so a1 has gone in and something has come to rest here, some new number, let us say b1. Now, I am going to insert a2. Now, a2 is greater than or equal to a1. So, can it displace a1? No, because it displaces the leftmost number that is strictly greater than a1. So, it will displace something which is to the right of a1, and therefore, it will displace something that is greater than or equal to whatever a1 displaced, right. So, it will displace something greater than. So, at the next row as well, the thing that I will be inserting, if at all, either it will come to rest at the end of this row, or it will displace something which is greater than or equal to whatever I inserted here. So, what will happen is that at each stage it will displace something that is greater than or equal to what was bumped out at in the previous insertion, and finally, it cannot bump out this b1, because it would have bumped out something bigger than b1 from the previous row, if at all, or it would have come to rest on the right of this. So, the new cell introduced by a2 is always going to lie in the row of the new cell introduced by a1 or in a row above it, which forces it not to lie in the same column. That is it. So that says that the cells will come in from, so the cells will somehow be replaced from right, from left to right as you insert A1, A2, A3 and so on. They will be introduced from left to right in different columns, okay, strictly from left to right. Now, how do I reverse this algorithm? So, for this I need to know which cell was added last, which cell was added before that and so on, to reverse it step by step. So, if this was the first box, then the next box the possibilities are here, here or here in this case, but not here. Okay, and now suppose I have a, I know that I have added 3 boxes. So, I had this thing and I know that I have added 3 boxes, say this, maybe this and this. These are my new boxes. Now, if the question is what order were they added in, then obviously this was added first, this was added second and this was added third. So, if I want to reverse my algorithm, I should first remove this box using the bijection from here, then remove this box and then remove this box. So, again the whole sequence is uniquely determined, and that is why this gives a bijection. And what is the application to representation theory? Oh, well, maybe let me state the dual of this. So, the dual theorem is CKA and cross tab star and the reasoning is actually very similar. The statement is the same, horizontal strip. Okay, so it is still horizontal strip, but these are dual tableau. So, when you actually draw when you put lambda equals lambda prime and think of them as tableau, you will get a vertical strip. So, I can rephrase this as saying that CKAN cross tab lambda AN. Yeah, what I am saying is this is bijection. So, here it is a bijection. So, the function is u comma w goes to, so you would if yeah. Yeah. No, it is a dual tableau, sorry. So, it is a column. Sorry, yeah, tab. Thanks for. So, if u is this thing, u is ak minus 1 a1, then this thing will go to. So, let us write it like that. Goes to, first you column insert this, then you insert this and so on, and you finally insert A1 is a bijection. So, that is the theorem. And what this gives is Ck an cross replacing lambda by lambda prime mu minus lambda is a vertical strip of length k. Replacing lambda by lambda prime. And what is the definition of vertical strip? You just replace column by row. And the implications for symmetric function theory and representation theory are what is really called the Peary rules. S lambda. Now recall that this rows, the generating whatever the rows are used to define complete symmetric functions, right. So what you are saying is S lambda times HK is sum over mu minus lambda is a horizontal strip of length k S mu, and the other second Peary rule is S lambda E k is mu minus lambda is a vertical strip of length k S mu. Yeah. Yeah, you get exactly the same thing, because a horizontal strip and a vertical strip coincide when you add only one box.
If you have a word with some row decomposition and then you insert it into a tableau, and then you find the column leading word of that tableau, and then you column insert it, you get the same tableau.
No. Okay, so these are the Peary rules, and in some sense, you know, these will let you, if you know how to expand Schur functions in terms of complete and elementary symmetric functions, then these will let you compute the product of two Schur functions. But those expansions of Schur functions in terms of complete and elementary symmetric functions involve negative terms, and in that sense these do not satisfactorily answer the question that I stated yesterday, that if I multiply two Schur functions, I want to expand it again as Schur functions, what do those coefficients count? So, they are positive and negative terms, so it does not satisfactory, but in principle you can definitely compute S lambda cross S into S mu if you can write S mu in terms of HK, for which there are formulas again involving semi-standard Young tableau. I will not go into that, but you can look at my notes from last year's workshop where this was explained. And what does it say in terms of representation theory? Let me just give you that. So, for this we need a little more of this dictionary between symmetric functions and representations. So, what we have is S lambda corresponds to the irreducible representation V lambda, or maybe it is called V lambda in this course, and E k corresponds to the exterior power wedge k C n, and H k corresponds to, because this wedge k and sim k are functors, these are representations of GLN, right. And these are the characters of these representations. In other words, if you just take a matrix x 1, x 2, x n and see how it acts on wedge or sim, and then compute the trace, you will get the complete or elementary symmetric polynomial. This is quite easy to see. If you haven't done it, you should definitely check. So you take a matrix like this in GLN. I'll just call it X. Then you compute the trace of X for its natural action on wedge KCN. So you know what a basis of wedge KCN is. It's like EI1 wedge, EI2 wedge, EIK, where I1 less than I2 less than IK. Right. So this will get multiplied by xi1, this will get multiplied by xi2 and so on. So this basis vector will get multiplied by xi1, xik. And when you add over all these basis vectors, you will get precisely ek. And if you do it for sim, you will get hk. So those are pretty easy. And so what it's saying is that if you take the representation V lambda and tensor it with sim k or with wedge k, what you will get a sum of representations, distinct representations, whose highest weights, which are just partitions in this case, are obtained by adding a horizontal strip. So what we are saying is maybe more consistent notation. Okay. And now I can introduce the also, I think Sridhar did it yesterday. There are two correspondences, the Robinson-Shenstedt correspondence and the dual Robinson-Shenstedt correspondence. What do you mean?
No, as in one can describe V mu just using mu. But now that we know it's coming from V lambda.
Right. So you maybe what you want to know is an explicit linear map, linear isomorphism from here to here, right? That would be a nice thing to have. So this is sort of a combinatorial shadow of that. So while there may be a way to do it, it's just saying that it's just giving, it's actually giving a bijection between a basis of this space and a basis of this space. But if you just take basis vectors to basis vectors, I don't think you will get an isomorphism of representations. You can try with k equals 1 and see what happens. Okay, so now what we are another aspect of what we have done is we can start with any word, and we can kind of run these bijections starting with, as Raghavan suggested, nothing, starting with the empty tableau, right. So then what do you get here? Okay, we are not inserting, say we are inserting a row in this case, but suppose we don't insert it, suppose we just take, so let me define two tableau. One is called, so I will define two functions, P from an star to tableau of any shape, an, and how is this defined? It's a1, a2, ak goes to, you start with the empty word and then you insert a1, then you insert a2 and so on, and then you insert ak. So, you sequentially keep inserting these numbers, and this will give you a tableau of some shape which I do not really know right now. The domain is an star. You could do it with rk as well. Yeah, an star, yeah. So, k is the length of a word in an star. So, you can do this with any word. If you do it with a row, what will happen is you will just get that same thing back, a1, a2, ak. And if you do it with a column also, you will get the same thing, right, if you do column insertion. But if you do this with a column and do row insertion, then you will get a1, a2, a3, ak. So, you will get the reverse word in fact. Yeah. So, this is a construction, but of course, so can we reverse this algorithm? No, this is not a row. So, let us just do an example of this. So, sorry, maybe I can erase this. So, what do we need to do to reverse this algorithm? So, let us just start with some word here, 3 1 2 1 1 3 4 2 1, and so first I will start with 3 and then I will try to insert the 1, right. So, it will push the 3 down, then I put the 2, then I try to insert the 1 into here. So, it will push this 2 down, this 2 will push the 3 down, right, and then I put another 1 here where it will just come here, 3, then 4, then the 2 will push this 3 down here, and then the 1 will push this 4 over here. Huh? Oh, 2. What? Something like that? Okay. But suppose I give you this, how will you recover this word? Well, as such, I think there are many different words which can give you the same tableau, because you do not know which. So, if I would know how to start if I know the order in which these letters got inserted. So, if I knew, for example, that at the last step this 3 was inserted, if I knew that, then I could reverse it, right. And if I knew that at the step before that, what was inserted the step before that, perhaps this 2, right, then I could again reverse that. And if I knew that at the step before that, this maybe this thing was inserted, then, so if I knew the order in which these boxes appeared during the insertion process, then I could reverse it. So, we could keep track, as we are doing this process, we could keep track of the order in which these boxes kept getting added to the tableau. So, if you remember what happened here, so first we had the 3, so there was a box, there was a single box, then we added a new, let me just do it again. So, first at the first step we have just 3, right. So, the shape is just this. So, I will write 1 in this box. Then at the next stage this 3 got pushed down and 1. So, the new box that appeared, the box that appeared second is this. okay, then the box that appeared third is this. So, as we are doing this, let us also keep track of when the boxes are appearing. Then I add this 1, right, and so that bumps this 2 and that bumps this 3. So, this is the fourth box to appear, and then I add this one more 1. So, that just comes over here. So, this is the fifth box to appear. I add a 3. So, this is the sixth box to appear. I add a 4. This is the seventh box to appear, and then some funny stuff happens. This 2 goes up here, and so the 3 comes to rest here. So, this is the eighth box, and then when I add the 1, this, so this is the ninth box. So, if I keep track of this data and I have this, then I can reverse the whole thing. So, I would say, okay, first this 3, this is the last box to appear. Where did it come from? Well, it was bumped up by this 2. Where did that come from? Well, it was bumped out by this 1. So, the last letter of my word was 1. So, I would have like, I could reverse one step and then I could reverse the next step and so on. So, then I would be able to reverse the steps. So, this thing, okay, the way we have entered it is such that at each stage we have added a box, and this box was added in such a way that the new shape is again is the shape of a Young diagram. So, what this kind of a thing. So, obviously, you cannot add a box if you do not have a box to its left or if you do not have a box above it, right. So, each box appears later than the box to its left and later than the box above it, unless it is in the first row or first column. So, what you are saying is that these rows and columns are in strictly increasing order, and that the numbers 1 to 9, each of them appears exactly once. So, such a thing is called a standard tableau. So, a standard tableau of shape lambda say lambda is a partition of D. So, this notation means that lambda is a partition of D, is a semi-standard Young tableau of shape lambda, where each of the numbers one to D appears exactly once. Of course, this is a somewhat perverse definition, because it is easier to define a standard tableau. It is just a filling of the boxes of a Young diagram with distinct numbers 1 to D, such that the rows and columns are both strictly increasing. You do not, it is symmetric with respect to rows and columns. So, this yeah. So, or in other words, rows and columns are strictly increasing, and there are no gaps in the numbers that appear, and no number is repeated. Exactly, each number appears exactly once. Okay, so that's, so what we are getting now is the following. So, now we should have this, and we should also keep track of this. And what will be the shape of this standard tableau? It will be the same as the shape of this semi-standard tableau. So, both these things should have the same shape, and once they have the same shape, I can reverse this process and do everything. So, I get a bijection here over all partitions in this bijection. Both sets are infinite as I have written it, but you could just take words of length D, then you would get sum over union over partitions of D. So, this denotes standard tableau and here it is not a n, it is just lambda. The letters have to be the size of the partition. So, even if n is only up to 4 here, I got numbers 1 to 9. So, there is no a n here. This is called the Robinson-Shenstedt correspondence, and there is a dual of it. It is called the dual Robinson-Shenstedt correspondence.
Know both these Venn diagrams, how we are getting that word.
How do we recover the word? Let me just do the thing as an example. Okay, so we know that 9 was the last thing to be. Okay, so I will erase this. Now I don't know what the word was. Okay, but I assume you've written it down in your notebook, so you can check if I get it right. So okay, so 9 was the last letter to be entered. So I know that this 3 came last. So then this 3 must have been bumped up by something here. So that would have been over here. So what I would have had is 2, 3, 3, and then this 2 would have been bumped up by this 1.
Is there any simple processes to enter those?
Nope. So you just have to do this. And now the next is this 8. Do you really want me to do this?
Yeah, no, I
Okay. So well, maybe I'll do one more step. So this 8 and then so that means this 2. Okay, so that means this 3 was bumped up by somebody. Who could have bumped up this 3? 2 or 4? I get confused. 2 because you have to So then this 2 was the previous guy, and then you delete this, and then you put 3, and then you look for the 7. So okay, that's that. Then you look for the 6. Well, that's that, right, and so on. So you will get back the original word. There's no these are algorithms. So these are bijections defined by algorithms. And there is a dual version of this. And in this, what you will do is you define, so this P, this thing is called, okay, so now I don't want to call this P, P was the previous thing, this is called RS, okay, and this thing is called, so this semi-standard tableau is called P of W, right, that is what I called it. It is called the insertion tableau of W. So this is called the insertion tableau. And this other guy is called Q, and it is the recording tableau. So in this RS of W, we write it as P of W, comma Q of W. So this is called the insertion tableau, and this is called the recording tableau, because it records the order in which things happened.
Does this have a representation?
Yeah, I will come to that in a minute. And the dual Robinson-Shenstedt, for this you define P star maybe we will do it the other way, AK minus 1, A1 is, so first you take A1 and column insert it into the empty word, then you take A2 and column insert it, and so on, and you take AK and column insert it. So you do column insertions, and this will again give you a tableau, and then you can also define the Q star tableau, the recording tableau in this case. So, just for fun, let me do it in this example. Well, some people's idea of fun. So, so we have this this column insertion is my weak point. I am good at row insertion, not so good at column insertion. But I think it's always good to think in terms of the pictures of the semi-standard tableau and work with columns from bottom to top. So, at the first stage I have 1, I am inserting this 1, and then I am inserting 2, and then I am inserting 4. Then I have to put a 3 in here, but the 3 should, I guess, displace the 4 and send it to the next column. So, anyway, let us also record the order in which things happened. Then, so then the 1. So, now I want to insert this 1, it will take this 1 and send it to the next one and remove this 4 here. So, this is 5, and then I have another 1. So, it will again just push this 4 out, and then I have a 2 which will push this 2 out, which will come to rest here, and so 7, and then I have this 1 which will again just push this, and then I have the 3 which will push this 3 over here. So, you see the P star tableau is the same as the P tableau, but the Q star tableau is not. We will prove that the P tableaus are the same a little later, but for those who are already deep into this game, you can try to solve this problem. What is the relation between this tableau and this tableau? So, so this is the dual Robinson-Shen state correspondence. So, what is it? It is just A n star, we will call it R s star. So, the way it is written here, this lambda would be the, if I started with the same word, this would be the conjugate word as a word, but the picture would be exactly the same. Okay, so, these are two different Robinson-Shen state correspondences, and it is intriguing what that the Q tableau are different. So, and it is also intriguing that the P tableau are the same, and that I will give a very nice explanation later on. So, what I am saying is that the dual so you will get a different word. Okay. So, the word that you will get will be 321 321 114 as opposed to 3322 11114. The words will be different, but when you draw out the tableau they will be the same. Okay, so that's the thing. So, what is, as you asked, what is the, well, I will give you the symmetric function interpretation of this. So, a symmetric function interpretation of this is something we are getting closer and closer to path models, as you will see now. So, so application to symmetric functions. So, the question is, let us take this correspondence, right. Can I tease out a Schur function from it? So, I have all kinds of words, and maybe I just take the sum over all possible words, and then I will get various tableau of all different shapes but can I isolate a single set of words which give rise to a complete set of tableau of shape lambda? Well, the answer is, if I fix q, I look at all the words with a given q, then I will get each tableau of shape lambda exactly once. So, it is a section. So, let me just write it down, the result. So, S lambda of x, well, let us write x lambda is equal to sum over W in A n star such that Q W equals your favorite standard Young tableau of shape lambda. Okay, so I'll just so this 0 means your favorite, and this is a standard tableau of shape lambda. So, your favorite standard Young tableau of shape lambda. So, this is my claim. So, T 0 lambda is your favorite Young tableau, standard Young tableau. Sorry. Okay, and since every Young tableau is somebody's favorite, it means you take for every standard Young tableau of shape lambda, you get a realization of the Schur function. So, so let me just illustrate this in a small example. So, let us look at lambda equals 2 1. So, we need, and let us take n equals, say, shall I take n equals 3 as well? So, how many words do I have now? I have quite a few words, right? Maybe I should take n equals 2. How many words of length 3 in 3 variables? 27, right? The first letter can be any of 3, the second letter can be any of 3, and so on. But I want only words which give rise to, okay. So, let us just take n equals 2 for example. Okay, so how many words now? I will have words of length 3. So, I will have 8 possible words, but I want the shape to be 2 1. So, I'll look for words. Obviously, those words cannot be rows or columns, but other words should probably give shape 2 1. So, let us look at all the words of length 3 in 2 letters, right. So, I can have 1 1 1, but that is not going to give me its p is going to be just a single row, right. So, let us not take that. 1 1 2 also will give me a single. So, I want all the words which give such that p of w has shape 2 1, right. So, let us take 1 2 1 2 1 1, I haven't fixed it yet. So, your favorite one will appear here, or we will just see everybody's have different favorites, so they will all appear. So, these are a couple of words, and then there are maybe words like, no, that is a column, so that is not going to work. So, so how many are there? 2 1 2, is that it? Words which are neither rows nor columns in 2 letters. These are the only 2, 2 211 is a column. Oh, 211 is not a column. Great. Okay. Yeah. But and 221. And anything else? Nothing else, right? 112, no. 122, no. Yeah. So I think this is it. 111 and 222 are no. So let's compute the Robinson-Shenstedt on these. So maybe you can tell me what is P and what is Q. So here it is 1, 1, 2, and in what order did they appear? It is 1, 2, 3. Is that right? First 1, then this 2 goes here, and then the 3 bumps. So this appeared last. Let's look at this. So here it is, first the 2 comes in, then gets bumped by the 1, and here we get 1, 2, 3. Right, and here we have first the 2, but the order is 1, 2, 3, and here we get, but the order is 1, 3, 2. Okay, so if your favorite tableau is this one, then you get S lambda of S21 of x1 x2 is equal to. So now I must pick the words which have this Q tableau. So that means these two, right? You will get x1 squared x2 plus x1 x2 squared. If your favorite tableau is 1, 2, 3, and if your favorite tableau is 1, 3, 2, then also you get one of the words with weight x1 x2 squared and one of the words with x2 x1 squared, right. So maybe it is more illustrative if I write down the tableau corresponding to these things. So V of the words are 1, 2, 1 plus V of 2, 2, 1, and here it is V of 2, 1, 2 plus V of 2, 1, 1, and this corresponds to 1, 3, 2. So you get two different realizations of the Schur function, and what you should view them as in the context of the Vishwanath's and Raghavan's courses is that these are two different path models for the same representation V 2, 1. So this in two variables, how do you take that in the path models? Yeah, okay, that's the rank GL2. Yeah. So if you take the group GL2 and write down path models of the kind, okay, so maybe we can do this in the tutorial, which is that you, okay, maybe Digjoy can, oh, he is not here, okay, you are here, okay. So you can write down the two path models corresponding to this. It is very simple, there is just going to be one, so you know in that context what to do, right, you have to apply these operators to the path models. So this is a path which will move in the direction, in a certain direction first, and then another direction and back in the first direction, and so on. So these are the paths.
Will count this square after defining fixture?
No, you just do it with paths. Yeah. So that will motivate the definition of crystals for Tableau. So that's it. So you can imagine that you have a more complicated thing, and then you would have many such Young tableau, and for each standard Young tableau, and for each of them you will get a different model for the representation V lambda. Okay, but the question remains, how are we going to motivate, how are we going to compute without using the, so in the in Littleman's paper, there is no notion of Robinson-Shenstedt correspondence in this manner. There is no way to take a path and then get a semi-standard Young tableau from it and then a recording tableau. So this section doesn't exist, and the way it's done is, it is done by taking one of these paths, maybe the one with the dominant weight, so in that case this one, and then you do something to that path and then magically you get this path as well. Okay, so you apply one of the operators EI, or is it FI? FI. You apply F1 here and you will get from here to here. You apply F1 to this, to this, then you will get from here to here. To this. Yeah, so what you will get is F1 applied to this will give this, and F1 applied to this will give this. So that's the little check you can do during. It's a quick one. I don't think it will take very long. So so maybe this is as good a time as any to stop. I have 5 minutes left, but maybe if you have questions, or maybe I can do.
Here in the RS correspondence, we start with empty set.
Yeah.
If we had fixed some tableau, this instead of empty set.
Yeah. That's a very good question. So so it's a very nice question. So what you're saying is, we start with tab, say we fix some tableau. Okay, so we have RS, but now it is based upon some W, which is already a tableau. And what it does is, it takes AN star and it goes somewhere. So what does it do? You have W and you have A1, A2, AK, and where do you send it? You send it to, this is what you are suggesting, right? Insert A1, then insert A2 and so on. And of course, you will get tableau which extend this one, right. So, tableau extending W. So, I guess you will get shapes lambda. So, let us say tableau of shape lambda. Then here you will get mu contains lambda, tableau which extend W, and what you will get here are standard skew tableau. So, the order in which things appear will form what is called a skew shape. So, you will get something called standard tableau of shape mu minus lambda. Yeah. So, what does that mean in terms of symmetric functions? We will maybe come back to that later. It has. So. Yeah, I am not completely sure, because this extending W, if that condition was not there, then these would be semi standard skew tableau. So, yeah. Yeah. So, you do column insertion and then you still keep the recording tableau. Oh, which one? Knut's one.
Where you count every element as less than or equal to.
That works by row. So that's actually, yeah, they're related via some involution. So yeah,
That's the same.
it's related. I wouldn't say it's the same. Yeah. You just reverse the order of the letters,
So
and
if
then.
you do dual insertion, conjugate shape and then conjugate it back, you will.
I guess so. So I'm not. So the thing is, this is interesting because if you want a tableau here, this would be a tableau of conjugate shape to this. So this is related to the dual RSK correspondence. Like Knuth defined two correspondences, and one of them is related to this. So remember, in the dual RSK correspondence, you read the entries in a somewhat funny order and so on. So, yeah.
That's on bytecode.
Yeah, yeah, but then you create a word for the, you can create two words from it and look at it that way as well. So that's that. Yeah. Okay, so I'll stop.